mess. So thankfully, then you can define that router right here at the bottom by saying app.use. So we're using a specific router, and it'll only have the needed. Then router that helps because let's add some real car data. Right here, an array where we can have a couple of objects with an ID like 1, a make of the car, like let's do a Toyota. We can do a model, 20,000, change S, year 2023, year of. What do you an array? And return all the cars. You can give it a shot by opening up the app in the browser and heading over to localhost 3000 API v1 cars. Now you'll see that I have an extension opened that renders all of that JSON in a nice format. You can find a simple Chrome extension, something like JSON Viewer, and that should work on your end too. But otherwise, it's going to look something like this. It is just an array of different objects. Perfect. Now what you could do is also implement all of the other functionalities. For example, getting a car by ID. I'll take this code right here and put it in the second place right after get all cars. And think a bit about it. How would you get a car with a specific ID? Well, first, you would have to know that we can get the ID from rec.params.id, as I explained before. You would also have to know that everything that we get through the params is in a string format by default, which means that we have to convert it into a number if we want to do some comparisons with it. Then we want to find a car that we're looking for by running cars.find. We want to find a specific car where its ID matches the ID that our user is searching for. If there is no car, then we can return some kind of a res.status of 404 and the message of car not found. Else, if we can find the car, we can simply return it by saying res.json car.
Hey, still thinking about joining the 30-day Python using AI bootcamp by AI for Techies? So what if in 30 days you could go from
Now back within our application one, but a nice try to figure out 2, 1. Okay, how would we implement this post route? It would look something like this. We make a post request to, we'll have to, that is the access to pieces of browser, it makes a GET request. But to make a post request, you'll need some kind of an HTTP client tool. It can be Postman, Insomnia, or in this case, I'm using HTTPy. Here, you would type 3000, right, for localhost 3000, API v1 cars, just to verify that our API is working, and we can see that it is. But now, here we have the options to also make all sorts of different requests, like a post request, where we can pass the additional body into it. In this case, we're passing JSON, and as we know, we have to pass a make, a model, a year, and a price. Perfect. So this HTTP client will have made an HTTP post request to our server, a new car object, by increasing its ID to be the new one in the list. We specified all of its variables, and then we pushed it to a car array and returned the newly created car. Pretty cool, right? Situation is pretty similar for the updates too. So if you wanted to update a car, that would look something like this. You would first figure out which car you want to update. You would then find the index of the car you want to update in the database. If it doesn't exist, you would return a 404, car doesn't exist. Else, you check whether you have provided all the fields needed to update it. If they exist, then you make the modifications to the car in the database, and then you simply return the updated car. And finally, there is a delete a car request, which is even simpler. You again have to get the ID of the car you want to delete. Then you want to find the car. If the car doesn't exist, you return a 404. If it does exist, you simply remove it from the array. And with that, you've implemented a very simple API with a non-persistent database. One part that is missing right here is some kind of logging, because as your API grows, you'll want to run certain code for every request, such as logging, authentication, caching, rate limiting, or performance tracking. Doing this inside of every single route would just be a mess. So instead, middleware solves this. Middleware allows a specific portion of your code to be called before or after any single request that a user makes. So right here on top, let's add a middleware. You can do it by running app.use. You get a request, a response, and the next object. This next object is what makes middleware, well, middleware, because middleware has to know when it's ready to move the action to the next API call in line. That's what we use this next object for. So, for example, let's create a middleware that simply logs out the timestamp of when a specific request is made. So const timestamp is equal to new date, and we want to get access to the ISO string. So dot to ISO string, and we want to console log it in this format by first rendering array signs, timestamp, and then we want to also render the rec.url as well as the rec method so that we know what the user is doing. Now, every time somebody makes a request to your server, you'll be able to see it in your terminal thanks to this middleware function. Let me show you. I'll open it up, and immediately, as soon as we load localhost 3000, you can see that somebody made a GET request to the root route. But there is one problem. You can see that we never provided the next functionality to this middleware, which means that it intercepted our try to get to the root route and stop there. It simply logged its thing, and that's it. What you want to do instead is whenever your middleware finishes doing what it's supposed to do, in this case, log the timestamp, the method, and the URL, we can simply call the next method and allow it to continue going where it needs to go. So now, back in the browser, it simply immediately middle request in this format by first rendering array signs, timestamp, and then we want to also render the rec.url stamp middleware next object. This next object is what makes middleware, well, middleware, because middleware that's so con, and we want to get access to the ISO in this format, what the user did in your terminal, and immediately get required the next functionality, root route, and stop there. If middleware finishes doing what it's supposed to call the, so now, request, but then on cars, functions, station, error handling, performance. Now, features like rate limiting, bot detection, or user abuse prevention are all things that developers attempt to build manually and then quickly regret it. That's why throughout this course, I'll show you how to use ArcJet properly so you don't just build, but build in a way that's safe, scalable, and production-ready APIs. Basically, ArcJet provides these protections with clean middleware APIs.
I saw that my PR got approved, but there was a test failure, and I have become so lazy. Like the moment I'm like, oh, I've got to go into like build kite and like look at the test logs. It's just like So I can just click into this.
Since we'll be using it both on the front end and back end, go ahead and create your free account right now. The link is down in the description. You can click sign up for free, sign in using GitHub, and you got your site key, which we'll use later on to secure our application. So in this one single lesson, you've built a complete REST API. And not only you've built it, but along the way, you've learned what Express is and why it remains the industry standard. You learned when to use Express and when to choose some alternatives, how routing, parameters, methods, and status codes work, how to structure routes cleanly with routers, how to build CRUD operations, how to parse JSON bodies, how to add middleware for shared logic, and how real APIs are shaped in production. But there's one huge flaw in the API we built, and that is that your data disappears every time your server restarts. So if you go ahead and add some cars, then restart your server, and then try to get them inside of an array, they die. For that, PERN stack comes in. A database is far more than a hard drive where your data sits for decades. It's a full system engineered to store, retrieve, protect, and organize information in a safe, consistent, and insanely efficient way. A proper database handles many users accessing the same data simultaneously. It keeps everything consistent even when errors occur. It allows you to search millions of records in milliseconds, ensures nothing is lost if hardware fails, and it even manages indexing, caching, transactions, and concurrency behind the scenes. It's not just storage, it's a data engine. So when people talk about databases, you'll almost always hear two categories: SQL and NoSQL. Two philosophies, two models, two very different ways of structuring data. SQL stands for Structured Query Language, a language created in the 1970s and still the backbone of modern data systems today. A common misconception is that SQL is a database. No, it's the language databases use to communicate. SQL databases organize data into tables. Think spreadsheets with rows and columns. Every table has a schema, clearly defining what fields exist, what types of data do they store, and how tables relate to each other. Most popular SQL databases are Postgres, MySQL, Microsoft SQL Server, or Oracle. SQL databases are ideal when your data has relationships and structure. Think users, accounts, transactions, merchants, or companies. These aren't just loose documents. They connect to each other through clear relationships. SQL databases handle this beautifully. A database is far more than a hard drive where your data sits for decades. It's a full system engineered to store, retrieve, protect, and organize information in a safe, consistent, and insanely efficient way. A proper database handles many users accessing the same data simultaneously. It keeps everything consistent even when errors occur. It allows you to search millions of records in milliseconds, ensures nothing is lost if hardware fails, and it even manages indexing, caching, transactions, and concurrency behind the scenes. It's not just storage, it's a data engine. So when people talk about databases, you'll almost always hear two categories: SQL and NoSQL. Two philosophies, two models, two very different ways of structuring data. SQL stands for Structured Query Language, a language created in the 1970s and still the backbone of modern data systems today. common misconception is that SQL is a database. No, it's the language databases use to communicate. SQL databases organize data into tables. Think spreadsheets with rows and columns. Every table has a schema, clearly defining what fields exist, what types of data do they store, and how tables relate to each other. Most popular SQL databases are Postgres, MySQL, Microsoft SQL Server, or Oracle. SQL databases are ideal when your data has relationships and structure. Think users, accounts, transactions, merchants, or companies. These aren't just loose documents. They connect to each other through clear relationships. SQL databases handle this beautifully. They also guarantee correctness through constraints, foreign keys, unique indices, transactions, and isolation levels, which in simple terms means that operations are either complete fully or not at all. Nothing's partial or corrupt. This so-called ACID compliance is why industries like finance, healthcare, and e-commerce rely on SQL systems. But hey, what about NoSQL? NoSQL databases take a very different approach. They shine when data is unpredictable, schemaless, or semi-structured. And is why initial or corrupt are either level, complete fully, or not at all. Nothing's partial or corrupt. This so-called ACID compliance is why industries like finance, healthcare, and e-commerce rely on SQL systems. But hey, what about NoSQL? NoSQL databases take a very different approach. They shine when data is unpredictable, schemaless, or semi-structured, and it spreads across many servers or it changes rapidly. Think logs, analytics, caching, or event streams. This is why many real-world systems use both SQL and NoSQL. A company might use Postgres for user accounts and business logic, MongoDB for flexible content, and Redis for caching and sessions. This is called polyglot persistence, using the right tool for each job. But when learning full-stack development and when building the vast majority of practical business applications, SQL is the ideal foundation. Okay, so we've decided. SQL it is. But which one? MySQL, SQL Server, Oracle, Postgres? Among all SQL databases, Postgres stands as the most powerful, modern, and open-source relational database in the world. Developers consistently rank it as the most loved SQL database, and not by accident. A couple of reasons why it's so great is that it's truly open source, so developers can use it freely for commercial apps, startups, or even cloud platforms. It has many cool features, supporting data types like JSON, arrays, IP address types, and even custom types you define. You get flexibility without losing relational structure.
So I can just use ChatGPT, right? Why do I have to attend your workshop?
See, that's the biggest misconception.
It also includes built-in full text search, window functions, common table expressions, and advanced indexing, which means you can express incredibly complex logic, which includes you get flexibility without IP address types and startups or even source. So a couple of reasons why it's so great is that it's truly open source, so developers can use it freely for commercial apps, startups, or even cloud platforms. It has many cool features, supporting data types like JSON, arrays, IP address types, and even custom types you define. You get flexibility without losing relational structure. It also includes built-in full text search, window functions, common table expressions, and advanced indexing, which means you can express incredibly complex logic with elegant queries. It's also serious about data integrity, so it's fully ACID compliant, protecting your data from corruption. It has great performance, best in class, handling joins, aggregation, and complex queries efficiently, even with large datasets. And it also has a legendary community. Documentation is great, tutorials and examples are everywhere, solutions to almost every problem already exist, and modern AI systems work beautifully with Postgres' structured data and metadata. So for modern web development, especially for learning, Postgres gives you enterprise-grade power for free. But here's what most tutorials don't tell you. Knowing what a database is doesn't make you ready for real-world systems. Your database isn't just storing rows. It's handling connections, locks, indices, query planning, background jobs, caching, concurrency, and traffic spikes. And when something slows down, breaks, or behaves oddly, you need to know exactly why. This is where developers separate into two groups. Those so-called vibe coders who hope everything works, and engineers who understand their systems end to end. And the new AI-driven world you're entering rewards the second group. This is where I want to introduce you to Site 24/7, which gives you real-time visibility into your Postgres server and your backend. It detects your slow queries, CPU and memory analytics, disk performance, connection usage, transaction behavior, and even spikes and anomalies. So whether you're deploying a side project or preparing a production app, monitoring is not optional. It's part of building real software. Since later in the course, we're going to integrate proper monitoring using Site 24/7, let's go ahead and create an account right away to make our job easier. Click the Site 24/7 link in the description and then start your free trial. You can simply sign in using Google. And then when you're in, you'll be able to see something like this, which means that very soon, once we start building our big PERN app, you'll be able to implement all of these features within it. And now that you know more about databases, it's time to learn the P in the PERN stack. Before you write your first SQL query, you need a mental model of how Postgres stores information. Once this structure clicks, everything you do afterward becomes far more intuitive. Think of Postgres as a multi-level hierarchy. First, you have the database server. This is your Postgres instance running on a machine. One server can host multiple separate databases. Each database is its own container for data. Your car dealership app might have one database. Another app might have a completely separate one. They don't interact. Inside every database are schemas. By default, everything lives in the public schema, and most applications use that without needing anything else. Inside schemas are tables, the core of SQL.